magnets. All about magnets. And magnets, like I would say it, are a very funny thing, right? They move objects or move other magnets without even touching them. And that's always been the big question, why? As in the video we saw, magnets are used basically in everything that makes our life easier, okay? And so, they're, oh! That's strong. That one with Willie Hood. Well, so anyway, how about I try it this way? So, as you can see, for those of you at home, I don't know if you can see that really that well, but these magnets are about the same diameter as a dime, and I don't know, half-inch thick or so. Okay, but they are strong enough to where my hand in between them does not keep them from trying to attract one another. Okay. Now, as you just saw, bad idea. All right. Who wants to give this a whirl? Come on up here. Come on up here.
What is the goal?
You're gonna separate them.
Oh, okay.
Okay, that wasn't supposed to be that easy. Okay, go sit down. Good job. She had leverage. Well, now come put them together, huh? Anyway, these types of magnets are called neodymium magnets. And I've got various sizes of them. Just got to locate them because multiple classes use them. So I'll get those out and found eventually, and then we'll kind of take a gander at them. But as you saw, they have a very strong magnetic force about them, okay? But then you get to the magnets that are on your refrigerator, okay? And those things barely stick at all. And so the various makeup of magnets is really what drives this level of magnetism that the magnets have. And so throughout this chapter, we're going to look at, how do magnets work? Where do we see magnets? What's the purpose of magnets? But also calculate, magnetic fields and everything like that, that are going to be found within magnets. With this chapter, I also have a brand new lab again. So I'm going to get that out. The lab we've used in years past has been, okay. But I'm anxious and excited to see what this new lab has, because I want to see some better results. Everything was good on paper with the last lab. Should have been nice. We did get basically everything to work on it, but it was very hit or miss. And so I'm hoping this new one steps it up a little bit. But anyway, we're going to be going through this chapter somewhat quickly, okay? You really don't get into your first math, I don't believe, until like the last second to last or last section of this chapter. So, for reals, y'all. So after this chapter, again, this should be done, I believe, well before spring break, which is good and bad. Bad being that when we start the next chapter, it's probably going to be split into 2 parts. But I've got to try to see if I can't finagle the schedule to where, we end, let's say, on a quiz before spring break and then go about it that way. I gotta work some magic there. But once we get into our through this chapter, we are going back in the book. And I know I said this before, we're going back to chapter 7, where again, we're going to re-encounter some motion, but we're going to look at different types of motion. We're going to look at centripetal, circular motion, okay? Then we're going to get into a couple of different concepts to round out the year. Isn't that weird to say already? Round out the year. But 9.5 weeks left. Anyway, let's talk about magnets and magnetic fields. In this first section, we are going to predict whether magnets will repel or attract each other. Describe the magnetic field around a permanent magnet and describe the orientation of the Earth's magnetic field. For tonight's homework, you do have 2 worksheets, but they're short, okay? So I'll hand those out to you after we get done with these notes, and these notes aren't very long either. So let's start off by talking about magnets. They attract iron-containing objects. That's a big thing right there. Attract iron-containing objects, and they have 2 distinct poles, the North Pole and the South Pole. And they are derived this way based off of the behavior on Earth. Like poles of magnetics repel, unlike attract. That first slide was going way back to probably 3rd grade. Now we start getting into new terminology. Magnetic domain. A magnetic domain is a region composed of a group of atoms whose magnetic fields are aligned in the same direction, called a magnetic domain. So again, as we saw in the video last Friday, it all comes down to the atom, and more specifically, the what? Electrons. Okay? And so this notion right here is very important to know. Fields that are aligned in the same direction. That's going to come through a concept a little later in this section that I'm going to bring up. It's not necessarily in your books, but it's always find it fascinating. Anyway, some materials can be made into permanent magnets. We've got soft and hard magnets. Soft magnet materials are iron. They're easily magnetized, but given enough time or an event, they'll lose their magnetism very easily. Whereas you have hard magnetic materials like nickel, they tend to retain their magnetism. Yes? Magnetized? Yes. Yes, and they'll retain it much longer. In fact, I believe we saw them when they the Alnico magnets, where they basically put them into a big chamber and they magnetize them. That's basically what it is. Magnetic fields is a region in which magnetic force can be detected. And if we were to utilize a compass, y'all know what a compass is? I'm just asking because who knows these days? Okay. What's a compass? Okay. Which there's a reason why I don't have it out, the ones we have out currently, because some of them, the needles are painted wrong, so it'll be going the wrong way. So I have to go through those and pick out the correct ones. But anyway, that's how compasses work. They use the Earth's magnetic fields to help direct you towards which direction you want to go. Typically, they'll point to the north, and then you can thereby kind of set out your course. But there's a reason why, and we'll learn here in just a few moments, why they point to the Earth's north. Okay? Anyway, as you see here, the red section, the red arrow section of a compass, that would be indicative of north. But why is the red pointing to the south on the magnet? What's that? Opposites attract, okay. But why on, like literally, why on Earth is the red, what does the red point to the north? If it's pointing north, wouldn't that mean that it would be pointing the opposite direction? They repel? See this picture right here.
So like on Earth, why would the red?
Yes.
Because then there'd be the light.
Ah, see? One thing we want to note from this image right here is the direction of flow of the magnetic field. And it was also stated in the video on Friday. it goes from the south to the north and out the north, and essentially forming cycles. Okay? South to north, out of the north, back around. It's important to know, especially for tonight's homework. But what do you notice in terms of the collection of field lines? Towards the poles, you have a tighter and greater amount of magnetic field lines, right? As you go on the side of the magnet, as you go further and further away, what do you notice about the distance between those fields? They become greater. Okay, so obviously the statement you can come up with is the further away from the magnetic source, the fields become further in distance, with the greater accumulation still being at the poles. So the Earth's magnetic field, I'm going to answer that question from last slide, is similar to that of a bar magnet. And I have the question of will it flip and consequences. I'm going to come back to that here in a second. Yes? Forget I ain't do it. Literally, this next point right here. The magnetic South Pole is actually near the geographic North Pole. And thereby the magnetic North Pole is near the geographic South Pole. So if we go back to the slide now, this would actually be the geographic North, and this would be the geographic South. So that's why the north end of the compass points north, because it's really magnetically south. And so I asked this question about, will it flip? And what I mean by flip is, will these poles flip? And yes, they do flip. There's been kind of a range of time frames, how long it takes. Some say 100,000 years, others say 300,000 years, some say maybe even more. To where the magnetic north now becomes the geographic north. And we have evidence within the Earth itself that this has occurred. And they're estimating within the last 35 to 40,000 years was our most recent flip. And when a flip occurs, the magnetic field weakens. And this flip doesn't happen like that. It itself can take hundreds and hundreds, possibly more years, to finalize the flip. So what kind of consequences do you think would happen or would be present when we have this flip occurring and we have a weakened magnetic field around the Earth? What do you think? Yes. Very good. Very good. I'm going to come back to that. You say? Yeah. Minnie? Yeah. Travel in what way? Okay, so in the whole process of it finding flipped, you can't do a direct 180 and, kind of go that way. You're going to kind of be held in limbo, possibly. Okay? And who knows about, migration patterns of animals. But going back to the solar winds. So yes, solar winds are going to have a great impact, but not only solar winds, but the amount of ultraviolet light that would pass through, which in turn, obviously be very bad for living organisms, but also when you have an increase in UV radiation, you're also going to have an increase in overall temperature. And they are kind of relating the last flip with the kind of the Neanderthal period. And so there's still obviously a lot of research and studies that have to be done, but that's kind of where they're leaning towards. So we're going to come back to this idea of evidence and flipping and everything like that. Then we talk about magnetic declination along with this. Basically, magnetic declination is a measure of the difference between north and the north that is indicated by a compass. And depending upon where you are located on Earth, your declination will change. At some locations on Earth, your north, as indicated by your compass, is going to be true north. Other times, other locations, your north that's indicated by your compass is not going to be true north, as we see with this image. Again, our poles aren't necessarily going to be, quote unquote, aligned vertically. Okay. Again, here's our geographic North Pole, geographic South Pole, and you see our magnetic poles are tilted ever so much. And so, again, depending on where you are here, you may be off by 10, 15%, or you may be spot on. So I want to go back to this. This was a big indication of the flipping of the magnetic fields on Earth. Has anybody heard of the Mid-Atlantic Ridge? Okay, you've heard about the Mid-Atlantic Ridge. It's located, well, in the Mid-Atlantic. There's also another one called the East Pacific Ridge, I believe. Anyway, what it is, it's this essentially this huge crack that runs along underneath the ocean. Okay, and it's just constantly moving and having magma, love saying that word, constantly creeping out here. Okay, well, over time, obviously, these plates are moving and they're moving away. But as they are moving away, that magma is coming up and solidifying and still creating essentially more land as it does so. But magma is rich in, what do you think? Iron. Yes. And so they discovered that while they were kind of dragging some equipment that was able to detect magnetic fields, what they found was they had these like stripes or striations along the floor where this Mid-Atlantic Ridge was. And so as you see here by this color coding, that the orangish reddish colors, those were your normal magnetic polarity as we see it today. The white stripes, not the band, but the white stripes on here, that's reverse magnetic polarity. As that magma comes out and is hardened by the water, the magnetic domains line up according to the Earth's magnetic field. And so they saw over thousands, millions of years, this pattern to where almost like every other stripe would line up with the magnetic fields of Earth currently. And the lines in between were flipped. And this is one of their best evidences to support the notion that magnetic fields do flip, and they can measure the time frame by how fast those plates are moving apart and the width of each strand, each band, if you will. So again, I find that pretty fascinating that the Earth is essentially keeping its own record of how it changes over all these times. And it was a fairly recent discovery in terms of science, well, because we just didn't have the technology yet. Speaking of technology, what was I going to say? I believe, now I've already shown you this video in honors camp, okay? But just listen again. We've got a few minutes. I'm going to actually stop the recording now, Okay, but if you've ever had an MRI, and I don't need to know if you've had an MRI, just if you have, okay,